Alright, we're going to begin Unit 4 that goes through gas laws. And already in Unit 4 you have looked at a series of different demonstrations that have basically modeled the different variables of gas laws that we're going to look at, such as pressure, volume, and temperature. Alright, so we're going to look at Lecture 1 under gas laws in your notes. Make sure that as you listen to this lecture that you follow along in your notes and record as many notes as you would like. That will help you to learn and understand gas laws, how they work, and be ready for a quiz that you will have. So like I said, what we're going to do is we're going to take what we saw and learned from those demonstrations and more or less apply it here. Apply it here to this tutorial. So,
Adam King, please come.
So we're going to start out with our essential question that needs to be addressed for this particular Lecture 1. The essential question is, what are the relationships between pressure, volume, and temperature of a gas? And so when you're done with this lecture, you should be able to answer this question and know it so well that you're able to take a quiz on it in next class period. Alright, so let's begin. Let's talk about pressure and what pressure is, what creates pressure, and so forth. So first of all, a simple idea of pressure is the fact that pressure is an equation that deals with force, or the amount of force that's exerted on a particular amount of area. So we can write an equation of pressure, P for pressure, is equal to force over area. And the units for force is the Newton, and for area it is cubic meters, or squared meters, squared meters. So those are the units of pressure. Then pressure has units of Newton meter squared. Okay, and we'll talk a little bit more about those units here in our next question. Alright, so the units of pressure. There are going to be a few different units that we're going to deal with. Of course, we already said that a Newton meter squared, 1 Newton meter squared, are the units for pressure, which is also simplified to equal down to what is known as a Pascal, or 1 Pascal. So Pascal is abbreviated as a PA. We can further use units of atmospheres. We know that 1 atmosphere, ATM, is equal to 101.3 kilopascals. This is a very useful unit, kilopascals, in chemistry. And so you probably want to remember this, that 1 atmosphere pressure is equal to 101.3 kilopascals. And from here, you're able to convert between atmospheres and pascals. And so this is the one I would strongly recommend you learning. Another one is 1 atmosphere is equal to 760 millimeters of mercury. And I'll talk to you about what that entails in a little bit. Alright? Now what we're going to do is we're going to actually draw a model of pressure exerted by molecules. Now let me erase this. Let's look at this. If I had a beaker here, and our beaker is full of molecules or atoms. Alright, so this beaker is going to be full of molecules, and I'm going to draw these. These are going to represent our molecules. And our molecules have energy, so they're in constant motion. And they're moving around randomly. Moving around like so. And when these molecules moving around randomly, when they collide into the walls of the container, they're going to exert a force on that container over a given area. And the force that these molecules exert on that container wall creates pressure. So if you think about in our demonstrations when we looked at balloons, the gases inside a balloon, those molecules were moving around at extremely high velocities because of the amount of energy they had, and they were constantly colliding into the walls of the balloon, exerting a pressure on the balloon. And so that's why the rigidness of the balloon exists, is due to these molecular collisions on the container surface. So make sure that you can be able to model molecular collisions on container walls creating pressure. Alright, so let's look at some ideas here, some more on pressure. We got two diagrams here. What the first one here is showing you that the amount of weight or air mass that's exerted on the surface of the earth creates a pressure. And the pressure that air exerts on the surface of the earth is known as the atmospheric pressure. All right? And so let me write that down. Atmospheric pressure. So basically, again, the atmospheric pressure is the pressure that the surface of the earth feels due to the force or the weight of a column of air that's exerted by on a particular area. So for the earth at sea level, the earth experiences a pressure of 1 atm, 1 atmospheres, or what we said before is 101.3 kilopascals. And we can do this because we know, again, the equation for pressure is equal to a force over an area. And so a column of air at sea level has a mass of a force of basically 1 times 10 to the 5 newtons. Okay? And so if you divide that by the area of 1 squared meter, that would be equivalent to basically 1 times 10 to the 5th Newton meters squared, and which is really 1 times 10 to the 5th Newton squared meters is really equal to 1 times 10 to the 5th pascals. All right, so which is really equivalent to 1 atmosphere of pressure. So 1 atm is the pressure that's felt by someone who is at sea level, standing at sea level. You would experience a pressure of 1 atmosphere on you because of the amount of air, a column of air molecules that's basically colliding in with you at that type of pressure. And so atmospheric pressure is going to be affected by the amount of force that you experience. And so it's going to change based on elevation, which we're going to look at in just a minute. Now, over the next diagram is a barometer. A barometer is a device that measures the pressure. A barometer measures the atmospheric pressure. Traditionally, mercury barometers have been the most useful and widely used. Basically, how a barometer works is that the air mass that's above the barometer is going to exert a downward force onto the mercury, and this is liquid mercury or metallic liquid mercury that's in this container here. And when the force of the air mass pressed against the mercury is going to cause the mercury level to rise, and then what we do is we're going to measure the distance the mercury level has risen based on the amount of force the air mass has exerted on the mercury. And so at sea level, the amount of force that the air mass exerts on mercury causes a column of mercury to rise 760 millimeters of mercury. And that's where you get the idea that 760 millimeters of mercury is equivalent to 1 atmospheres of pressure. And again, that's going to change, that the distance that, or the height that the mercury rises is going to vary based upon the pressure that's exerted by the atmosphere. And that's going to be influenced more or less by the elevation. So how does elevation affect, how does elevation essentially affect the pressure? Well, it turns out that as you climb higher and higher and increase your elevation, that the amount of air mass above you is going to be less and less. So the amount of air mass exerts a smaller force at higher elevations over the same area. So as you increase the elevation, the pressure or atmospheric pressure decreases. And so that's something that's important to make note of and to remember, that as you increase in elevation, the atmospheric pressure itself is going to decrease. All right. So you can see here in this diagram, at the base or the sea level, the atmospheric pressure is 760 torr. A torr is the same thing as millimeters of mercury, so you can just say 760 millimeters of mercury or 1 atmosphere. But as you increase your elevation, the atmospheric pressure is going to decrease to basically 520 millimeters of mercury, according to this diagram at the top of this mountain here. All right, so make note of that. All right, now we're going to look at back to our essential question of how pressure, temperature, volume are all related in a gas. And so we've already demonstrated these in class with demonstrations, and now we're just going to put it together make some notes on these things. The first one we're going to look at is the relationship between pressure and volume. And this relation is known as Boyle's law. According to Boyle's law, as the pressure is going to increase, the volume is going to decrease. At a constant temperature. And this is known as a mathematical relationship. This is known mathematically as a basically inversely proportional relationship. And essentially, again, as you, at a constant temperature, when you increase the pressure, the volume of a gas is going to decrease. And so the idea is you, as inversely proportional, as you increase one, the other one is going to decrease. And this, of course, is known as Boyle's law. Alright, so we have a diagram of Boyle's law here, and you can notice from the picture here, in this first beaker here, we have two weights here, and as the weight has created a certain volume of gas, which is located down in here, and then as you take off a weight, as the weight decreases here, the volume is going to increase. So again, we show a relationship from this graph, pressure 2 and pressure 1, volume 2 and volume 1. So this is our first point. First point, you add more. If you add more, actually, let's erase this so you can see this a little bit better. As we basically decrease the volume, or decrease the mass here, then our volume is going to more or less increase. And so we see this with Boyle's law as it comes down to it. As we increase our pressure, then our volume is going to get smaller, and vice versa. If we decrease the pressure, then the volume gets larger. Okay? And so again, that's an inversely proportional relationship. Here's another diagram of it. We have pressure of 1 atmosphere, and you can see the molecules colliding with the container, creating a pressure. But as the pressure is increased to 2 atmospheres, the volume is going to more or less get smaller. And if we even increase it to 4 atmospheres of pressure, the volume even gets smaller and smaller. So again, we see Boyle's law in effect here. The bottom line is just make sure that you understand that Boyle's law shows the relationship between pressure and volume. And as the pressure increases, the volume decreases. Right. The next is we're going to look at Charles' law. And Charles' law looks at changing the temperature but keeping the pressure fixed or constant. So Charles' law states simply that the volume of a fixed quantity of gas at constant pressure, so the pressure must maintain constant, is basically increases as the temperature increases. This is known mathematically as directly proportional. Okay, so essentially here, if we increase the temperature of our gas, the gas molecules are going to move faster and faster. And so they're going to collide with the surface of their container more often. And this is going to create start creating a greater pressure. But we don't want the pressure to change. So these gas molecules are going to be moving faster and faster, and they're going to collide with the walls of their container more often, creating a greater pressure. Now, we don't want the pressure to change, though. So with temperature, then, if we're going to increase it but keep the pressure constant, then we're going to have to increase the volume. Because as the volume increases, then the collisions of the gas molecules are going to be less often, maintaining the same amount of pressure and not an increase. So again, as we increase the temperature, the molecules are going to be moving faster and colliding with the container, and so it's going to start increasing the pressure. We don't want that to happen. We want the pressure to stay the same. So the gas has got to expand, and it's got to become a greater volume in order to keep the pressure constant. And so as temperature increases, the volume must increase, and this is known as being directly proportional to each other. All right? You can see this with this graph here, or diagram. More or less, we want to notice that the pressure is going to stay the same. We have one weights on each one. The pressure stays the same. The only thing is we're changing the temperature. It's increasing, and so therefore, as the temperature is increasing, so does our volume. Now there is an actual mathematical equation for this. And in fact, we need to go back to Boyle's law and look at the mathematical equation for that. But basically, you have the volume of the initial volume over the initial temperature is equal to the change in volume over the change in temperature. And so if you use this mathematical relationship, if you know the initial volume, you know the initial temperature, and you know the change in temperature, or the new temperature, then you can figure out the new volume using this equation, and which we will have you use in class and on homework problems. Okay, let's go back really quick to Boyle's law. Okay, so look at your notes really quickly. Back at Boyle's law, let me show you the mathematical equation for Boyle's law. It's basically if you have the pressure, your initial pressure, times the initial volume, that's equivalent to the new pressure times the new volume. And so again, just like you saw Charles' law, if you know the initial pressure, the initial volume, and you know the new pressure, then you can figure out what the new volume will be using this relationship or equation, which we'll also use in class. Okay. All right, so now this gives us to the combined gas law. And the combined gas law basically combines Boyle's and Charles' law together. So if we take pressure 1, volume 1 over temperature 1, and then pressure 2 over volume 2, or times volume 2 times over volume temperature 2. This gives us an equation for the combined gas law. And so here we can change pressure, temperature, and volume initially and figure out a new temperature, pressure, and volume here using this equation. So make sure you learn the combined gas law equation. All right, now, and we'll do some problems in class on that. Okay, so now what we're going to do is we're going to look at what is known as Avogadro's law. This is a really simple law. Basically, the idea is the volume of gas at a given temperature and pressure is basically directly proportional to the number of moles of gas. So basically, the more, what this is saying, Avogadro's law is really saying is that the more moles of gas you have, the larger the volume. So if I increase the number of moles, I increase the volume. If I decrease the number of moles, I decrease the volume. So it's pretty straightforward. And we know from previous working with stoichiometry, we know that at standard temperature and pressure, that 1 mole of gas is equal to 22.4 liters at STP, standard temperature and pressure. And so this has always been an important thing. Again, the more moles you have of a gas, the greater the volume of that gas. So make sure you know Avogadro's law. Alright, now we're going to look at the most important equation that we can talk about, which is known as the ideal gas law equation, sometimes known as the pervert equation. The ideal gas law is more or less PV equals nRT. This is probably the most famous gas law equation of all time because it essentially combines all of the components of Charles's, it combines Boyle's law, and it combines Avogadro's law all into one equation, important equation that you'll use often. So let's break down these variables. R is known as the gas law constant, and it's going to be 8.31 joules Kelvin mole. And if we use this gas law constant R, then the other units we have to know as well, which we'll look at. So for N represents the number of moles of the gas. T is the temperature, and the temperature must be in Kelvin. In fact, for all of these gas laws that we have gone over, the equations, we're always going to use Kelvin as our temperature deal. The volume is V, and our volume needs to be in cubic meters. So we may have to do some conversions. Just remember that 1 liter is equal to 1 cubic decimeters. All right, and that'll help you to do some conversions there. And then pressure, P for pressure, is going to be in pascals. Okay, so you can use pascals for pressure, cubic meters for volume, temperatures in Kelvin, moles is N, and then gas law constant 8.31 joules Kelvin mole. Make sure you're familiar with these units for the ideal gas law. We are going to do some example problems in class using PV equals nRT. Make sure that you have it down, memorize this equation, memorize it, know it. You just got to know this. This is an important equation and how to use it. All right? So that we will discuss some more later. All right, finally, we're going to talk about partial pressures. Now, this is really easy, I think, to understand. And basically, Dalton's law is what this is referred to. And Dalton's law just states that the total pressure is the sum of all the partial pressures of each gas that's in a container. So basically, the equation that we could say is that pressure total is equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, or plus whatever else, depending on how many gases are. So if we have 3 gases and we add up each of the partial pressures of each gas, that will give us the total pressure of our container. So we have a diagram down here. We have 2 gases, one in blue and the other one here in red. And you can see that under these circumstances, a 5-liter container, 20 degrees C, 0.5 moles of the gas, which is represented by hydrogen, has a pressure of 2.4 atmospheres. In our other container, we have 1.25 moles of helium at an atmospheric pressure of 6 atm. When we combined these 2 gases, helium and hydrogen, together into one big container here, then you can see that the total number of moles of gas is 1.75 moles if you add them all up. The pressure, the total pressure of both gases together is 8.4 atmospheres. And basically all we did was take the pressure total is equal to the 2.4 atmospheres from hydrogen, and we add it to the 6.0 atmospheres of helium, and that gives us a total pressure of 8.4 atms. Okay? So the idea then is it doesn't matter how many gases you have in a container, as long as the volume is constant, so we have a constant volume and a constant temperature. So constant volume, constant temperature, all the gases added together, their partial pressures is going to equal the total pressure that's exerted or is exerted on the container of the walls of the container or whatever it is. All right? So that's partial pressure for us, and we can ask any questions you have about that in class. All right. So that basically wraps up everything in this lecture, Lecture 1, about gas laws. Both Boyle, Charles, Avogadro's law, and partial pressures. I would very much encourage you to make sure that you've taken down really good notes, study those notes, study both Boyle's, Charles' law, Avogadro's law, understand what partial pressures are, make sure you memorize the ideal gas law equation, know the units for the ideal gas law equation, the R value in the ideal gas law equation. Make sure you understand the units of pressure and so forth. If you need to go back and relook at this video, do so at this time or later on. Also, go back to our essential question that we had. Be able to answer the question is, what is the relationship between temperature, pressure, and volume of a gas? And that is really important that you can answer that for the quiz that we will have in class. Okay, so this is it for now.